Okay, so what we're going to do now is we've completed the impedance measurements, the Z11 measurements using the vector network analyzer. So we're going to do some experiments in transference and see how we can transfer power between the transmitter and the receiver and the various loads involved, and how that corresponds to the impedance measurements that we took before. So just to explain the setup, first of all we're going to focus on what's going on with the generator and the various instruments, make some measurements, and then we're going to go over to looking at the experimental region with the transmitter and the receiver, and we'll do some various different types of experiments and transference. So to start with, just to explain the system, we've got the 811A vacuum tube generator here. Same setup as before, transmitter, coil with the tuning system. Obviously we've disconnected the vector network analyzer and we've reconnected the high voltage supply and the plate return back to the vacuum tubes. Power meter incoming to the high voltage transformer shown here. The yellow trace on the oscilloscope shows the voltage across the primary capacitor, which is obviously in parallel with the primary coil. The red trace shows the anode current, so we're using a Tektronix current probe here, which is connected through here to the oscilloscope, and at the same time from the voltage measurement we're also taking a frequency measurement on the Tektronix universal counter. So now by using the remote control as per normal, this is the remote control that controls the power to the input to the transformer. We can turn on. We can see from the power meter there's about 300 watts of power going into the high voltage transformer. Here we are on the 2 kilovolt scale, which gives us about 700 volts anode voltage, and obviously this is showing the voltage for the heaters, for the tubes. That's all fine. Move that up to about 300 watts again. Anode current is 600 milliamps RF, and I'll just show you how the experiment looks a little bit further down. I'll just pan around slightly. You can see the load there is fully lit. It's quite bright. We're going to take a look at that in a bit more detail later on. Just for the current flowing down here through the single wire arrangement, that's 130 milliamps RF. Those are two Western 425 RF ammeters. So coming back to the measurement area, we've got just over 300 watts worth of input power. We are measuring, this is 500 volts for division, so the total oscillating voltage over the primary is in the region of about 1,500 volts peak to peak. And the current here, well, we're on 10 millivolts per division, and that corresponds to 1 amp per division. So we have got about a 1 amp anode current, pulsed anode current. Obviously it's only in the positive cycle, and we can see that that is pretty much approximately 90 degrees out of phase, representing that we are not resonating the primary in this situation. We are not running it at the resonant point, and it looks predominantly as an inductive load. Therefore the 90 degrees phase of current and voltage in the primary. And frequency, now we have this wound, I believe, fully closed, so it's around about 1200 puff, 1200 picofarads, and we can see from the frequency counter we're reading 1.699 megahertz. That corresponds to the frequency being shown here, which is measured from reading 1. I'll just pause it for a moment. 1, 0.695, so there's a good correspondence between the two, down to tens of kilohertz. Just set that to run again. So that's at 300 watts. So what we're going to do now is we're going to adjust the tuning and see what impact that has on the frequency. So I'm reducing slowly. We can see the frequency is rising, 1.72. This represents oscillation at the lower frequency, 1.74. It's getting a little bit unstable, jumping around. You can see from the oscilloscope we can no longer treat this accurately. We're now in an unstable position. Let's just take some more averages. Okay, I've got 1.76. 0.77. There we're starting to get to balance point. It's going to try and want to jump up there. It's going to watch here, it's going to want to, and here it's going to want to try and jump in frequency up to the upper. Keep increasing, 1.82. Increasing. Current's power's fallen off considerably. Okay, we're at very high frequency now. I think it's almost fully open. And now we've settled down at the upper frequency, which is now reading at 3.38 megahertz. So now we are stably oscillating around the upper frequency. That was above the phase change. Lower, there, 2.0 megahertz, as measured on the, raise it, 3.3. There we are flipping between one and the other, between the lower points of resonation and the upper. This corresponds here as well. It's 3.32, 3.31. Again, drop it down and go through a transition. 2. That's the upper limit of the stability of the lower resonant peak. That was the lower frequency, which is below the 180 degree phase change. Reduce the clap there, jumps almost straight away. That also corresponds to a change in the difference in the experiment, of what's going on in the experiment, and we'll look at that in a minute. I want to illustrate those two frequencies, transition between the two. Now when we were winding up there was a fair amount of stability. I'm going to go down in frequency again. There's a fair amount of jumping around there. That frequency reading is not necessarily accurate because it's gone into burst. That is, the valves are switching on and off in a more uncontrolled fashion, because the impedance is quite high and we're not actually at a defined resonant frequency. This is the disadvantage of using the vacuum tube as an oscillator. There are indeterminate places, such as this place, where you can't really get a good feedback signal, and hence good, strong, clear oscillation from the generator. If you were driving this with a linear amplifier, which we will do another time, then we would be able to control this more accurately directly through the frequency range. Go back down. Now we're getting stable again, more stable. That's it. And we could see the frequency is dropping as I increase the load capacitance on the primary of the transmitter. It's 500 watts there. Just pull that back down again to about 300 watts. And that's back where we started. So again, we'll have another go at that. So we can start increasing reducing the capacitance. Try and keep the power at about 300 watts. There we're entering that unstable region again. Start jumping around there. We keep reducing the primary capacitance there, is still in that unstable burst type region. We'll have a little bit more of a look at that in detail on the oscilloscope in just a moment. Just going to go back up to that stable point. Power's dropped down. We'll just pull it up a little bit again to about 300 watts input power. Until we hit that second higher stable oscillation frequency. There we are. We're now stably oscillating. Again, the power's gone up again because we've hit a resonant point. So we're just going to take that back down to about 300. Drop back down again. Look for that flip between the two. Currently we're 3.25 megahertz. No, back into the unstable region, so we probably need to go a little higher. Keep going up. We may have missed it. 3.7, 3.8. Starting to reach the useful range of this type of vacuum tube generator. 4.2. There, it's really, now we have reached the maximum useful, become unstable again. We go back down into that, there we are, 4.2 megahertz, we're in that upper oscillation range now. Still about, just reduce the power a bit. Quite a lot of anode current up here, it's almost an amp. RF current. Come back down again. It'd be nice to find that flip point between the two. It swings between one oscillation and the other. It's around about 3.1. We're looking for the frequency counter to flip suddenly and stably to the lower frequency. Tricky to find that point. Go back into that unstable place. See if we can go up slightly. 2 there, it seems stable. The load is lit here in the single wire. Let's just see if we can accuracy. Switching so cleanly this time. Adjust the power slightly to find a stable point. Down to 200 watts. We're back into the lower frequency band now. So we've got the power slightly, reduce. unstable point, which strangely enough is actually the point of best balance in terms of the transference of electric power, but because of the way in which the generator is driven, that is as an oscillator, it appears the most unstable point from the driving. But there we are, we're up at the upper frequency again. I'm going to lock that in position. We're just 300 watts, it's almost 1 amp, 980 milliamps of RF current. Still a little bit jumping around on the oscilloscope. We'll push it a little bit further into the stable point. 2.3, there we are. A bit more stable now. Just keep that on about 300 watts. Don't put too much current through the meter. It's just over an amp now. And there's about 130 milliamps. 125, 130 milliamps of RF current flowing in the circuit, and we've got a good stable oscillation there at around about 3.3 megahertz. So that again illustrates moving from the lower oscillation to the upper oscillation in this transmission experiment, and we see what all the instruments read and how we could use the instruments to show us what's going on. So let's go back into that unstable region, and we see and have a look on the oscilloscope, and we'll see what it looks like in that band. So let's drop down a bit there, where the frequency counter shows some very high frequencies. There's a burst type things. Let's go and see what we could see here. Okay, so that's why you see we're getting bursts of power coming from the valves. The valves are switching unstably. Try and stabilise that a little bit. We can see the envelope. So there it's jumping between bursts of power and trying to stably oscillate. That's because the impedance is of the circuit is much higher. The slope of the phase is quite a lot in this region of the characteristics, and it's difficult for a good solid feedback signal to the valves to establish a good stable oscillation. And that's why we're jumping around in that region. Although this region, from the point of view of the experiment in the transference of electric power, actually represents a very interesting point. Just bring us up to 300. You see there's a lot less current flowing. We're barely at 300 milliamps RF anode current. I mean, we're right at the bottom end of that meter, which is a logarithmic meter, very much at the bottom end. So we're just on the scale, and there's no discernible current flowing through the experiment at this time. So down a single wire between the two. The bulbs are not lit. I'll just show that. The bulbs are not lit at all there, and there is no current flowing through. Yet there is, and there's very little going on at that point. Mainly because the valves can't stably oscillate. In other words, quite a bit of the power is being dissipated in the valves, or being reflected back to the valve, so we can actually see even that the anode plates are getting hot. They're starting to glow a little bit red. You won't be able to see that on the camera, but take my word for it, they are starting to glow, which means quite a lot of power is being dissipated at the tubes, and not much of virtually nothing of that power is actually going into the transmitter, through the transmission line and out the other end. So in other words, we are at a point here, as far as the vacuum tubes are concerned, of poor match. away from this point. Let's bring it down to the lower, get it stable again. There we are. Now we're back somewhere a bit more stable. Power's quite high. We're going to just ease that off a little bit. Just let the valves cool down a little bit. And there we are. Just get that triggered again. Look at that. Yeah, we're largely back where we were. And you can see now there's, well, if I adjust that down a little bit, try and keep us around about 300, we're back where we were. So about 600 milliamps of RF power in the primary, 130 milliamps in the single wire connection. I'll just pan the camera over so we can have a look at that. Okay. Little bit of glow here from this one. There's more from this one, but this will become more apparent when we move the experiment to have a look at what's going on there. And oscillating back again where we were at about best part of 1.7 megahertz. Okay, so now we're going to have a look at the experimental region itself. So we're looking at the transmitter there. This is the adjustment for the primary capacitance. The equipment is off currently. So we're going to turn on. That brings us back to where we were. 300 watts input power, 600 milliamps RF primary current, and about 130 milliamps single wire current. And we can see that we're getting a nice glow off of this. You usually get a bit of a spark coming out the top of this. No, yeah, there's a little bit of sparks coming off from my finger there. And that 100 watt load is lit fully. So in other words, if I were to connect that load correctly to the main supply, which is 240 volts, 50 hertz here in the UK, that would light to about the same brightness. So we're putting 300 watts into the transformer. We're lighting a 100 watt load by a single wire. And we have a load connected at the receiver as well, which we can't see at the moment. I'm going to show you that later as well. So what we're going to do first of all is look at the effects of frequency. So we are stably oscillating at 1.7 megahertz, and that's at the lower frequency, and the bulbs are quite well lit, so I'm going to start progressing up slowly now, reducing very gradually the capacitance on the primary. Okay, so we see it's starting to get a little bit unstable. We're at 1.75 megahertz, 300 watts power. There, stabilized again. It's 1.7, almost 1.75 megahertz, 300 watts input power. Okay, 1.78 megahertz, 1.79. Power's dropped slightly. I'll just increase it to 300 again. 1.8. And we're also entering that unstable region now where we saw the burst waveforms where the valves couldn't start stably oscillating. Okay, so now we're in that unstable region. We see the switching going on in the experiment. There's the flicker. We can see the flickering at the top here. Even when I put my hand in, it's enough to change the tuning. That's how unstable it is. Obviously be careful not to touch the primary, but even putting myself in, bring it out, that's just how unsteady that position is. I'm just doing that at the receiver as well. Where that was the same point where we got the burst waveforms where the vacuum tubes weren't able to stably oscillate. Still at 300 watts, going to keep moving up now, okay. Okay, we're still in an unstable place. All the currents dropped off in the single wire, almost completely. We're still in that unstable region with the burst. Bring the power up a little bit. Okay, we're still reducing the primary capacitance to get back to the upper stable position. Right, there we are. Now we start to see that coming in. We start to see the bulb starting to light. That's it. Now we're at 3.2, still not stable. 3.3. Okay, now we're in a stable position. We at about 300 watts. Again, just over an amp of primary anode current in the transmitter. About 125, 130 milliamps RF. Not so much top end energy there. I'm going to keep winding up. So the energy's going to fall off. So there's now no longer any useful oscillation energy coming from the tubes. Winding it down more quickly this time. All the way back down. Okay. Okay, so carrying on, we're going to have a look at the particular modes of transference that are going on in the single wire region. We are back at the start point. We're at about 1.7 megahertz, 600 milliamps RF in the anode, 130 milliamps RF in the single wire, and I'm going to start winding up the frequency. It's 174.76, 1.77 megahertz, keep 1.8, keep us on 300, about 300 watts. Okay, we'll just go through that unstable region. Okay, there's no current now. No current in the single wire region. The anode current's dropped almost to zero in the generator. We'll just keep going up, get through this unstable spot into the upper. Okay, there we are, we're now at 1.9. So we're right at the top end. 1.98. We're right at the top end. We got 700 milliamps of RF current. Let me just drop that back to 300 watts. That's 650. Now we can see that there is the current flowing in the single wire is very low. The bulbs are very dim, but there is a lot of there's a lot of voltage tension, both here. Not much power there. But I'll also show you in the receiver. You see also that this is centre of the secondary is very well lit, and the load here, the two bulb part of the load here is very well lit. So in other words, we are putting the power, not dissipating the power here. We are transferring the power through the single wire and using it to power the load at the receiver at this end. What I've done now is I've brought the camera back so that we can see the whole experiment in one go. We are right at the upper end of the lower frequency band. Just going to stabilise it a little bit. It's quite hard to keep it at this point. Here we can see that there's a lot of voltage tension at the top end of the two secondaries of the transmitter and the receiver. There's very little power being dissipated through the single wire. You see very little power here. There is a little bit, it's not completely zero, but the load at the far end, in other words the load which is connected to the receiver primary, those are lit, fully lit. So therefore we are transferring that power all the way through and using it to light the load at the other end without losing very much in the centre. Let me try to adjust this so it could be a bit more stable. We go either side, so we keep going up. Right, so now conduction has stopped. We're in the unstable region. Going to go up. We're in the upper region now. So, no, sorry, we're in the lower region. This is the lower region. All the power is being dissipated, or the power is largely being dissipated in the single wire load. There's very little tension in the receiver, and there's very, very little power being dissipated in the second load at the primary. The bulbs, although it may be difficult to see from here directly, the bulbs are very slightly lit here. If I try turning the light off, you might be able to see that a bit better. Let's have a look. Okay, it's very difficult still to see. I think I'll pop the light back on. Okay, so we're going to wind up again now, go into the upper section. We're looking for that change in transmission mode. Okay, so here's an unstable point, but it's an interesting unstable point because the modes are changing in and out between electric field based modes and magnetic modes. The colour of the bulbs changes differently. It takes on a brilliant white. It's unstable because it's now very much in burst oscillation, but if I move it on slightly, there, now it stopped. We were right on the edge. There we're just coming into, so there we're stable. We're at 1.8. Raise it slightly, we're becoming unstable, unstable. There the modes are flashing in and out. There it's a transverse, a typical transverse. The bulbs are lighted normally. Here, now we've got a mixed mode. We're not just transverse, but we've also got a mixed longitudinal mode. The colour of the bulbs has changed to a much more brilliant white. Display that again. There, that's a typical transverse mode. The bulbs will be just running normally, warm, hot to the touch. I should think that dissipating power is being dissipated. Yeah, just a little warm. And then into this mode here. Now, that's a much more interesting state. there we have a brilliant white light emanating from the filaments. I just turn it down a little bit. And so there's the brilliant white illumination. I've turned the power down to 170 watts to help illustrate this. There's the yellow glow. There's the change in the white light. There. As we put a burst. Increase the power a little bit, 200 watts. There's the burst. There's normal illumination. It's a typical transverse mode, current is slowing down. Now we've got a mixed mode. Now we are at right at the top end of the lower band, 1.83 megahertz. Going to keep going up. We're in that unstable region where there's very little anode current. The oscillator is not really running. Keep going up until we flip into the higher. No, there we are, flip into the higher. Okay, we've got minimum dissipation here, but now we see the load at the far end is fully lit. There is a little bit here. The filaments are just slightly red. There's a lot of top end voltage, and we can see that the receiver bulbs are fully lit, and that's 200 watts. I take it down to 100 watts. We see the load is still lit at the end. There's now nothing in the middle. Bring it up again, 200 watts. We are still oscillating at 2 megahertz. We're still at the top end of the lower frequency. Up to 300 watts. Now we're going to keep going up. Okay, now we're at 3.3 megahertz. We are then dissipating power at the upper frequency in the single wire. So all the power dissipation is happening here, and there's no power being dissipated at the receiver primary. Keep going up, 3.4 megahertz, 3.5, 3.6, starting to reach the useful limit of this generator. You see power's diminishing. 4.3, 4.4, and that's it really. There's not a lot more to go higher than that. Bring it back down, 4 megahertz, 3.9, 3.7, 6, 5, 4, 3.3, and then we flipped. We're in that transition now between the 2 and the 3. This was where the balance point, it's the balance point where the electric and the magnetic fields of induction are in balance. The magnitude of the impedance on the graphs that we saw earlier are equal. And you could even see it transfer one side to the other. Now you see it's slightly brighter here. I'm going to wind down. Now it's getting slightly brighter there and dimmer here. So we've got that null. It's right where that null point is in the middle. So if we think about the standing wave that we formed there, that longitudinal magneto-dielectric impetus, we've got the balance point now, the null point in the center. Now these ones are brighter and these ones are dimmer. We're oscillating at 2 megahertz, and I'm going to reduce that slightly There they lit about the same, and now we're at 1.92. This side is lit brighter than this side. Now we're out of conduction. Bring back the balance point. There we are, we've got the null, we've got the longitudinal magneto-dielectric wave established, maximum voltage potential at the top ends of the two secondary coils, very little power dissipation going on, current has dropped considerably. This meter is, let's get it as clear, stable as we can. This meter has dropped right down to its logarithmic at the bottom, so it's right down to about less than 50 milliamps. It's not as pure as we'd like it to be, but if it were pure, these would be full brightness at the top ends of the secondary, the neon bulbs, and these would have no glow at all. Of course, we're not in an ideal situation. We're not perfect. It's an empirical experimental situation. Again, showing the balance there. We've stopped oscillation. Let's get it oscillating again. There we are. Right at that balance point. And that point is the optimum point for transference of power from the generator through this system to the load. And Tesla maintains that properly tuned, properly matched with connection of the bottom ends of these secondaries into the earth with very low inductance connections, that power could be transferred from one side of the earth to the other via this mechanism. Now we're seeing a little bit of how this mechanism was intended to work. That seems to be about the most stable point. We've got full illumination at the load. We're putting 300 watts power into the transformer. We're lighting the load fully at the other end. There's a little bit of dissipation in here. We might be able to tune the secondary. We might be able to tune the primary of the receiver just to improve that a little bit. Again, we're going through the balance point. It's stopped conduction. We'll just retune again from this side. See if we can get it any better. Okay, that's at 3.3 there. Right. That's a little better. That's a little better. So we're at, right on the transition. 2. If I go just another turn, we're going to be oscillating at 3.3. There we are. So the flip between 2 that we saw before by just a very slight change of primary tuning on the transmitter. Change it there. Now we're at 3.3. Change it back. Now we're stably at 2. Right at that top end, right at that balance point in between. Take it a bit further. That's stopped conduction. So there, stop conduction again. There we are looking at a tuned transmitter and receiver with a standing wave with a null point in the centre and demonstrating longitudinal transference of power between the transmitter and the receiver, so that you get almost all of the power at the far end in the receiver, and very little within the single wire in between. Now, of course, I mean, in terms of efficiency, we're working with 100-watt loads, and we're putting 300 watts actually into the transformer. So we are consuming a fair bit of power in this circuit, for example in the vacuum tubes, in the generator, in the transformer is getting warm here with the high voltage that it's generating. So we are not working here with a particularly efficient system. We are by no means putting 100 watts in and getting 100 watts out. But the power going in at this end, so in other words with all the losses involved with the generator and all of those things, then the power going in at this end, and then the power that we can extract out of the other end based upon the tuning and the position that we choose to tune it, whether it be at the lower frequency, whether it be at the higher frequency, or whether or not it's at the balance point where the electric and the magnetic fields of induction are balanced, equal, and then we can have that longitudinal standing mode, longitudinal magneto-dielectric wave established between the two coils. That gives us a good starting point to start exploring some of the more interesting phenomena that arise from the single wire, and also some of the Tesla radiant matter experiments, which we've seen and have been well demonstrated by people like Eric Dollard and others. Okay, so we're turning back on. We're still at the balance point. We're going to go away from the balance point, and we're going to flick up to the higher frequency. We're oscillating at 3.3 megahertz. We've got 300 watts input power to the transformer. We're in single wire conduction, normal conduction, so power's being dissipated in the single wire. There's no power being dissipated, or very, very little. There's a tiny, tiny glow on the filament, and we're going to pull that out. So now we've decoupled the transmitter and the receiver. Obviously the tuning has changed. We're still at 3.3 megahertz. We're going to do a bit of tuning, see what this looks like, but now we have nothing attached to the other end. And we can see the bulbs are quite well illuminated. I'm taking it up to 4.1 megahertz, wind it back down. Now it's a 1.9, we've gone through that transition. That's the 3.4, much more stable because you don't have the transmitter and the receiver interacting with each other. You're just tuning one end, literally. 3.3, jump down to 1.9. Doesn't really change the single wire current very much at all. It's about 120 milliamps. It's about just around 300 watts, 700 milliamperes RF in the primary. I can really wind this frequency around. There we're up at the higher, and it's completely stable. That's up at 4.1, up at the useful end of the generator. Wind it back down. There we are, 3.3, 3.2, 1.9. There, we flipped over that. You actually can't tune it into that balanced region. It just flips states between the upper and the lower. There's no interaction going on between the transmitter and the receiver, and it shows just how important it is to have the transmitter and the receiver tuned and balanced with each other, because then you form a cavity. You form a cavity for the generation of that standing wave, and hence the emergence of the longitudinal magneto-dielectric wave, which comes when you get that null point in the middle, which comes when you have the electric and the magnetic fields of induction balanced. So let's wind it back. It's just going to flip 3.3, We'll do 1.9 straight away. And a single wire conduction is in itself very interesting. We're going to do more on this at another time. I just wanted to illustrate what happens. You see, we've got plenty of voltage potential here, and we're dissipating current in the single wire with no obvious return. These are, I would think, warm. Yes, so they are dissipating power, but they're not roasting hot. Plug it back in. We are at 3.3 down to 2. Okay, now we're back down to that. Now we're back down to that optimal point. So high voltage tension on the top of the secondary, very little power being dissipated in the single wire, and the load at the output of the primary of the receiver is fully illuminated. Okay, we'll just add a bit more load there. See if we can improve transference. Okay, we're going to have to retune to get it into that position. No, actually we've now made it worse. By putting too much load on that end, we've now reduced the Q sufficiently that we can't actually get it oscillating in that balance point properly. There's a little tiny bit of power at the end, but we can't get to it. So we just take that out again, reduce the load slightly so we don't reduce the Q too much of the oscillation going on in the system. And there we are straight away. It was already at the right tune point. Load is lit at the end. There's a little bit of power being dissipated. The null is in the centre. There we are. You see the lightning, the brightening and the dimming of the bulbs as the null point moves through the centre here. There it's on there, it's in the single wire, flip it back, now it's at the load. So watch, it's a tiny shift. There it's in the single wire, there it's in the far point in the load. There it's there, 3.3 megahertz. Now it's in the far point, 2.0 megahertz. We're right in the transition between the two. There, it's even more. Now we're flipping actually between the two. Try. It's a very narrow band. Just a tiny adjust of tuning. There we go. Dissipation within the single wire. So dissipation in a far point in the load. Single wire, and the current in the single wire increases. Far point in the load, and interestingly, the single wire current reduces. Yet we're still able to illuminate fully the load at the far end. Load in the middle, load at the end, and the current drops as well significantly. It illustrates the difference between the transference modes that are going on between the transmitter and the receiver. What we would consider to be normal transference, that is a normal electric circuit, although of course you've got to bear in mind it's all via single wire, and then that specialized mode which comes from the longitudinal magneto-dielectric wave, standing wave in the cavity, which is also the precursor to displacement experiments. But we'll come on to displacement experiments at another time. Dissipating the power in the single wire and over to the load. also includes a jump in the anode. So in other words, there, got quite a high anode current, more than an amp. There we're dropping down to just over 600 milliamps, and yet all the power is appearing at the end. And we've got a good voltage tension at the top of the secondary. Push it back there, much less tension, and the tension's collapsed at the far end in the receiver. There, you can see that the top ends of the secondaries are about equally lit. In other words, we are holding the tension balanced between the two. Tesla maintains that this could be accomplished over any distance around the Earth, where the Earth becomes the medium with a single wire, so the Earth is a single wire joining the two, and of course you have a virtual Earth at the top of the secondary stack. There we go. Fantastic. And that's an introduction to the transference of electric power.